Hello everybody. Today we're going to be focusing more on a fairly simple question that we've actually sort of addressed in some of the last few problems. This is going to be finding the height of a binary tree. Now, we've done this problem several times in a simple way. We've done it in the diameter of a tree problem, if you guys recall that. I believe we also did it in finding a symmetrical tree problem, but we're going to talk about a couple different ways to approach this problem. Now, the first way that we did, usually I'd pull up a whiteboard for this type of tree problem, but today I feel like I'm probably just going to stick with the code representation since we've already have a pretty decent understanding of how a binary tree looks like and how we would approach solving this type of problem. The essential step that we did in the last problem is we used a recursive methodology where we start at the root. I think we're just going to start off by creating the function. So let's say our function is called tree height. We're going to start it with having a root, and what we're going to be saying is that if the root is none, we are going to be returning -1. Not -1, sorry, 0. We're going to be returning 0 because essentially when the root is none, we know that the tree is that we're calculating is empty, so we would just return a 0 as the result. That's pretty self-explanatory. Now, after that, what we do is that we calculate the heights of the trees of the left and right subtrees. So we're going to do tree height of root.left. This is the recursive function that we're calling, and right is equal to tree height of root.right. And then what we're going to be doing is we're going to be at the end returning 1 plus the maximum of left and right. The reason being, we want to see which subtree is bigger, and whichever subtree is bigger, that's the tree that we're doing. So for example, I'll put it down here. If we have a tree that looks something like this, 1, 2, 3, you see the root as 1, it has two subtrees. One is the left subtree, which includes 2 and 4. The right subtree includes 3. What we want to do is say we want to see which subtree is bigger, since in this case the left subtree is going to be bigger because this one has a higher height. We're going to calculate the height of this tree and then add 1 to the root. So first, and then when we're calculating the height of the left subtree, we continuously do the same thing, where we calculate this height of this left subtree since it's bigger than the right one. Well, the right one is none. So we're going to be adding that to 1, and then we'd add 1, 1, 1, and the total would be 3. So that's essentially how this code works, and of course, at the end we can, well, the code is already done here. We return the 1 plus max left right. We could test the code. I'm just going to copy paste this test case over here. Building the tree like something like this. Hold on. Shift tab. The output should be 3. This is wrong. So we have a tree that looks something like this. At the end of this, we're going to be returning, if we did this correctly, this is the recursive method, the height of the tree is going to indeed be 3. Alright, sounds good. However, one thing to keep in mind is that, for example, this function uses what is called recursion, which I'm sure by this point you're pretty familiar with what recursion is, where you're continuously calling the same function over and over. In this case, it doesn't add much to the time complexity. However, it does increase the space complexity unnecessarily because it continuously calls a function over and over again repetitively, and that can cause some problems. It might not be the most efficient way to solve this problem. So we're going to be taking a look at a better way to solve this type of problem. Give me 1 second. Now, let's comment this code out. A more efficient way that we could do this kind of thing is instead, this solution is doing what is called a depth first search, where we're continuously going from the left tree, and you might notice how in the left tree we continuously iteratively call the left function first, and then eventually when you have to, it calls the right function. What it does is it continuously goes downward to the left and left. This time we're going to be doing something different called a breadth first search. Now a breadth first search is instead of going down to the most lowest point possible and then eventually returning 1 plus the maximum left right, this whole entire process that we did here, what we are instead going to be doing is we're going to be going line by line, a level by level. So we start at the first level, increment 1 to the height, go to the next level, increment 1 to the height, and then do it until we get to the bottom level. That is going to be the overall process of how we're going to be doing this. And the way we're going to be doing this is first, we're going to be using something called a deck. Why are we going to be using a deck? Because a breadth first search approach primarily uses something called a queue, where a queue goes in by a first in first out method, also known as a FIFO method, where you take in the first element that comes in, which is the root, and you immediately take that one out, and you continuously do that each iteration. And you'll see more about what I mean by this as we start getting the code. So first, the class node is obviously going to be the same. Next, we're going to create the same tree height function. I'll probably just call it the same thing, tree height of root. Now, the same thing, what we're going to be doing is we're going to be doing starting if the root is none, then we're going to be returning 0. So obviously, if the root is none, we're going to be returning 0, just like we did in the first one. However, what we're instead going to be doing is we're going to be making a queue. So using deck, we can make a queue like this, and the first element that we're always going to put into the queue is the 1. So we see that if there is a root in the queue, there's like a proper root that we can append to the function, we'll add it into this queue. Next, we're going to start at the height as 0. So this is what I mean. We're going to have this height variable that's going to continuously increment over and over again. So while the queue. So what we're going to say is while queue. What does while queue mean? It simply means as long as there is an element in the queue the queue will stay. So we're going to continuously loop through the queue, and this while loop will continue running as long as there is an element in the queue. And what we're going to say is we're going to have a level size. So this is going to be a variable called level size, and it is going to be equivalent to the length of the queue. So right now it starts at 1. Now what we're going to say is we're going to do another loop. This time we're going to be looping actually into every element in level size, which is the length of the queue. So basically, essentially what we're doing here is we're just looping through the entirety of the queue. Next, we're going to say node. Why are we going to be doing node? We are going to be storing this into a variable, and this object is going to be the first element of the queue. Queue.popLeft, what it does is it takes this first element and it takes it out of the deck. So it takes out the first element of the deck, and it does this immediately. In a proper dynamic array, you wouldn't be able to take out the first element in the list. You would only be able to take out the last element of a list, which would make a dynamic Python list more equivalent to a stack. But this time, since we're doing a breadth first search, we need a FIFO method, so we are using a queue to pop out the first element of that of the queue, and we're storing it into the node. Now what we're going to say is that if this node we pop out, if there is an element to the left of it, if there is an element to the left of it, if node.left, it's the equivalent of saying if node.left is not none. We could also say is not none, but that's a lot of text, so I'll probably say if node.left. We are going to append that value into the queue. So queue.append node.left. We're essentially going to say, like, first it starts out as 1. We're going to pop out 1 from the queue and then add the next element into the queue. So node.left is in the queue, and we're going to be doing the exact same thing with node.right. If node.right queue.append node.right. And at the end of this loop, all we're going to do is we're going to be incrementing, not this loop is done, looping through the queue is done, but we're going to increment the height. So if we look through this code step by step, it's pretty simple what it's doing. We start at 1, the queue has an element of 1. Now we loop through every element in the queue. So for example, if we were on level 2, we would be looping through 2 and 3, but to start out with, we're just doing one loop. We're saying we check to see, we add the 2 in the list and we add 3 in the list, because that's we pop out the 1. So the next step of this, what was it gonna look like? So for example, it starts out, sorry, this one. It starts out with just being 1, but then we pop out the 1 and then it becomes 2 and 3, and then we pop out the first element of 2 and 3 and we add that to 4. And each time we're going to be each time we pop out an element, we're essentially essentially checking to add an element to the height. So we go level by level. 1 is a separate level, 2, 3 is a level, and 4 is going to be its own level. And we increment that to the height. We increment 1 to the height, and at the end of this loop, when the queue is completely empty, so we know that nothing is left in the queue because we're not able to do node.left or node.right anymore, we're simply going to be returning the height. Now, what is the advantages to this method? Instead of using the recursive method previously, where the space complexity would have been n, the space complexity would be n. This does not use any additional space complexity. In fact, the only space complexity it uses is the maximum width of the node. So it's going to be using the maximum width of the node. So for example, the worst case would actually be n. However, there is a scenario where in this time the space complexity would be significantly less than the entire thing, because in a recursive method we'd have to go through every single node has its own space. However, in this one, the queue, as you notice, it's never completely full. It's always going to be including only the elements of the level that we're on in the list, and that makes the space complexity of this method significantly less. So the space complexity is called actually big O of W, where W is the maximum width of nodes. I should write that down somewhere. Let's say here, time complexity O of n, space complexity O of W, where W is the maximum number of nodes at any level. So obviously there is a situation where the worst case could be big O of n as well. However, on average, this method is significantly less when it comes to space complexity, and that would be efficient for memory purposes when you're trying to run this code rather than this code, which has the same exact time complexity of O and n, but the space complexity is also going to be O of n, which in this case is more than the space complexity in here on average. So one last thing, let's just test to see if we get the same result using this list. And yes, we get the exact same result. Height of the tree, we did again. We could test this by adding another one to the left, I guess. Root dot left dot left dot left. We'll say this one is 6. And you see how we increase the height of the list. This is equivalent to like what would you say? How would you do this? Like, and then something like this, though. Yeah, so basically it looks like this now, and exactly the height is 4, just like we see here. So yeah, hopefully you guys understood the new and improved method for calculating the height of a tree. In summary, instead of using a depth first search approach, we used a breadth first search approach, specifically by using a deck. The use of a deck to use a first in first out method where we continuously append each level to the queue, pop it out when necessary, and increment the height on each level. So hope you guys understood that, and thank you for watching. All right, see ya.